All right, let's get into it. Today, we are looking at something pretty wild, a totally new blueprint for quantum computing called U-theory. And I'm not just talking about an incremental improvement here. This is a complete rethink of how we build these machines, and it basically challenges the entire industry's current approach. All the big players in quantum are locked in this arms race, right? Just trying to build bigger and bigger machines with more qubits. The whole assumption has always been super simple. More qubits equals more power. But what if that's just wrong? What if scaling up, just adding more and more, is actually leading us down a complete dead end? And this really gets to the heart of the diagnosis. U-theory's whole argument is that the problem isn't a lack of effort, it's that all that massive effort is being pointed in the wrong direction. It calls this the Sisyphus error, the myth, endlessly pushing a giant boulder up a hill just for it to roll right back down every single time. Why? Because the very foundation, the ground you're standing on, is unstable. So let's unpack this a little. This central problem. Why is the current quantum arms race, this whole obsession with just adding more hardware, potentially built on a massive fundamental mistake? Okay, here it is, laid out plain and simple. The Sisyphus error. The industry is trying to patch problems of quality and design with sheer quantity. You've got qubits that lose their quantum state way too fast. That's what U-theory calls weak form. Then you've got chips where the qubits can't really talk to each other very well. That's poor position. And the solution so far has been what? Just throw millions more of these noisy, error-prone qubits at it? That's the brute force action. And it's creating this profound imbalance in the system. So, if brute force is the problem, what's the alternative? And this brings us to the core philosophy of U-theory. It's not about chasing more power. It's about finding a smarter balance. And this is the crucial insight. U-theory totally reframes the challenge. The crisis in quantum computing today, it's not a resource problem. It's a design problem. The solution, it says, is an understanding and balancing these three core ideas: form, position, and action. Think of it like a three-legged stool, right? If one leg is way too long or too short, the whole thing just topples over, no matter how strong the other legs are. And this is just brilliant. It shows exactly how that philosophy maps directly onto the actual quantum hardware. Let's break this down. Form. That's the qubit's identity, its perfect, pure quantum state. The catch? The price you pay is durability. That state decays, it just fades away. That's decoherence. Then you have position. This is all about how the qubits are laid out, how they connect and entangle. The price here is distance. Moving information from one qubit to another costs you a lot in these things called swap gates. And finally, there's action. This is what the computer actually does, running gates, taking measurements. But here's the kicker. Every single action introduces noise. It creates errors. The current approach just hammers on action while pretty much neglecting form and position. So how do you actually build a machine based on this new philosophy of balance? Well, this is where the theory becomes hardware. This is where we get the U-core architecture. So over on the left, that's the standard approach. Every qubit is supposed to be this perfect, identical little soldier. But in the real world, trying to force that uniformity just creates a chaotic, unpredictable mess of noise. Now, look at the right. That's the U-core philosophy. It completely embraces the fact that not all qubits are born equal. It designs the chip with an intentional stability gradient. It specializes qubits based on where they physically are. Instead of fighting nature, it's designed to work with it. And this is what that looks like in practice, at least on their simulated 43-qubit chip. It's a set of concentric zones, this cool gradient topology. Right at the center, you have the core. This represents form. These are your most protected, most stable qubits. They're built for long-term quantum memory. Around that is the mantle, which is all about position. These are the super connected networkers. They're like quantum buses, just routing information around efficiently. And then on the outside, you have the crust. That's for action. These qubits are fast, designed for all the noisy work of getting information in and out of the system. Every zone has a specific job, and it's perfectly matched to its physical place in the grand scheme of things. Okay, so you've got this highly specialized orchestra. It makes sense that you'd need a pretty specialized conductor, right? You can't run this unique hardware with standard off-the-shelf software. It needs its own intelligent operating system. And here it is. It's called the Triadic Quantum Compiler, or TQC. Now, a standard compiler is, it's kind of dumb. It just tries to minimize the number of operations to make things run faster. The TQC is way smarter than that. It actually understands the physical geography of the U-core chip and uses that map to its advantage. So what does this quantum conductor actually do? Well, first, it reads the chip's physical map. Then it intelligently assigns tasks that need long-term stability, the really important stuff, to the super-protected core. It uses the well-connected mantle to move data around efficiently, which minimizes those costly error-prone swap gates. And then it pushes all the fast, messy input-output work to the outer crust, where it can't disturb the important calculations. See, it's not just optimizing for speed or gate count. It's optimizing for the overall health and stability of the entire system. Now, all of this sounds incredible in theory. I mean, an elegant design, an intelligent compiler. But does it actually perform any better? How do you prove that this isn't just a cool idea? The entire concept, the whole proof, really hinges on a single metric that they designed. It's called the stability index, or SIQ. And this one number is designed to measure the overall health and balance of a quantum processor, taking form, position, and action all into account at once. So, first, what's the baseline? What are we comparing this to? Well, based on the available public data, the stability of today's state-of-the-art quantum processors, the ones built on that brute force model, is estimated to be right around 0.40. Okay? Remember that number. And the simulated stability score of the 43-qubit U-core chip? It's 0.71. Yeah, just let that sink in for a second. That is nearly double the stability. And this leap forward wasn't achieved by adding thousands more qubits or inventing some kind of new physics. This comes from taking the same kinds of components we have today and just arranging them in a smarter, more balanced way. And that is the whole point. A better blueprint can be way more powerful than just bigger hardware. Look, a bold claim backed by a simulation is one thing, but U-theory actually takes it a giant step further. It puts its money where its mouth is, with concrete, testable, and completely open source predictions. And this is how you know it's serious science. The theory makes these specific, time-bound, and falsifiable predictions, things that can be proven right or wrong. For example, it predicts that the first compiler plugin for Qiskit, that's a really popular toolkit for programming these things, will be out by mid-2026, and that a real-world chip using this design will hit a stability score over 0.65 by the end of that same year. I mean, these aren't vague promises. They are public deadlines that the entire world can watch to see if they're met or missed. And what's more, the project includes something it calls an honest assessment. It openly admits the hurdles it faces, like the manufacturing paradox, which is the fact that our current chip foundries are all optimized to build millions of identical things, not the specialized, gradient-based chip that U-core needs. This shows it's not just hype. It's a serious engineering proposal that is fully aware of the real-world challenges ahead. And it all comes down to this final, really thought-provoking challenge. The theory argues that by focusing only on adding more and more qubits, the industry is basically staring at a cave wall and just calculating the properties of a shadow. The real solution, it claims, requires a fundamental rotation of perspective to see the object that's actually casting it. So the question this whole thing leaves us with is the quantum industry ready to make that turn?